All right, great. So last time I was here, we talked about how we take an ingot and begin to forge that ingot in a way to close up the porosity that's inherent to an ingot. And when we get to a break point, I actually brought an example of something that we forged at work that didn't go very well, and it has still, the porosity is still present, and it's very easy to see. It looks kind of like a piece of Swiss cheese. I also brought a few other show and tell items, so we'll get those out in a little while. Are there any questions about the material that we covered a couple of weeks ago as far as the metals, cogging, friction pyramid, anything like that we need to review? Okay. So we were talking about how do we close up holes in the ingot, and the term that we use for that in the industry is cogging. That's the special type of forge work that's done with the goal of closing up the holes. So we have this friction pyramid that we talked about, and this is a very important concept to understand because we said that it's virtually impossible to move all the metal under our die without causing a lap or other defect. We'll talk about that in a minute here. If we jump to this slide, here are our friction pyramids that we talked about. Here's our representation of the ingot porosity, and we want to close that up. And we said last time that that's only going to close up if you can get the point of this friction pyramid and the point of this friction pyramid to run into one another. So you have to do enough deformation to make that happen. If you do deformation but it's not enough to cause that to occur, your size, your overall size, your cross section will change, but you won't really have any effect here. And at this point in our process, this is what we're concerned about. So we have to make sure we're doing enough deformation to have an effect along the center line. We'll talk about some situations where that might not be feasible right away in our cogging process and how we manage that. Here's an example of some laminated metal that shows you these friction pyramids, and you can see the differences in layer thickness along the center versus up here. This is one where the friction pyramid has collided and caused deformation to occur here, and up here we still didn't have much effect. The friction from the die that's in contact with the work is still acting on this metal here and keeping those layers closer to their original starting thickness. So, if the regions between our friction pyramids are not worked, and what I mean by regions is not let me go back to here. I don't mean this space, I mean this gap between this point and this point. If this area is not being worked, then what do we have to do to make sure that it does get worked, right? If we get this properly forged so that these 2 points come together and these points come together and so on, that's great. We've got little regions along the center that have been collapsed and the porosity has been closed up, but we have these other areas that have not been worked yet. So how do we make sure they do get worked? Yeah?
You just do the same work on
Right. That's exactly right. So you'd make another pass, but you'd offset your second pass from your first pass so that now you hit the spaces that you didn't hit before. And you continue to do that until you've reached a situation where you've worked the entire length all along the center. Jump forward here. Whoops. So that's what we say overlap. We call that an overlap from one die bite. Overlap from we would say one side of the ingot. Typically what we would do is we would make a pass down the length of the ingot, and then we would rotate the ingot 90 degrees and we would make another pass. And so it would be pass number 2, which would be sort of staggered or offset a little bit from pass number 1. And then we would make a third pass after rotating 90 degrees, and that would be offset yet again. And we would continue to do that until we've worked the metal all the way down to the size that we need. But this kind of begs the question of, if we know we have to do that, can we quantify that and predict that so that we can set up a procedure that we know is going to be effective? And the answer is that yes, we can do that. So, and this is, I think, about where we stopped last week. If we I've represented our two friction pyramids that they've collided along the center, and here's the gap that's in between these two adjacent die bites, right? So the press has come down and squeezed here, and then we've moved over just enough, and again, so that these two die bites on the surface are right next to one another. There's no gap, even though at the center there is a gap. That's because of this effect of this friction pyramid. So, and this is where we get a chance to use a little bit of math, very simple math. And the equation I don't know I don't think it's here, but I'll tell you what it is. You can write it down. It'll be helpful for you on the homework. So we have the die bite, and that's the metal, the amount of metal, the length of metal that's underneath the die. We call that W. And the height here is just whatever the starting height of our material is. And we're going to assume that we have the square or round cross-section. If we have a die bite that is at least 1/2 of our stock height, right? Whatever the numbers are doesn't matter. The proportion is what's important. So as long as W is 1/2 of H, and the amount that we bring the dies together, we call that draft, that amount is 20% of H. If those two criteria are met, then this length here at the center, this is going to be 1/3 of whatever our W is, okay? So from that tells us that if we made 3 perfect passes that were properly overlapped and staggered down the length with these criteria, we should be able to close up all of the porosity along the length of the ingot. From that, we also can calculate that we would need a change in cross-section area. So if I had a 10-inch square, that would be 100 square inches. I'd need to reduce that by 3, so 33 square inches. If I do that, I should be able to close up all of the porosity, okay? That's kind of our ideal, yeah.
What are these equations again?
Okay, so the equation is if W equals 1/2 of H and the draft is 20% of H, then our dimension L here will be 1/3 of W. So if I have a 30-inch wide die and I take a full die bite, all 30 inches, and let's just say I'm using a 10-inch, if I use, and if I have a 10-inch cross section and I reduce that from 10 to 8 with a 30-inch bite, I'll have 10 inches deformed along the center line.
Okay.
Right? That's what that means. Does that make sense? Because we can review it again, or I want to make sure that's clear. Yeah?
What is the draft?
So draft is how much the dies come together. So that is to say, in this case, if my starting dimension of my workpiece is 10 inches, and to have the 20% requirement, I would need to bring the dies together so now that there's only 8 inches between the dies. Okay? Any other questions? No? Okay. So now, in this example, I should go back and just give a little bit of background on this. So this was actually, these equations were arrived at through some research that was done not at Scott Forge, but somewhere else quite a while ago. I found it in a paper. And in the particular situation that the investigator was researching, he was using a plain carbon steel, something like a 1045, and he was investigating temperatures that were between, say, 1900 and 2000 degrees Fahrenheit, okay? And I've used his research as the basis for what we do at Scott Forge because it allows us to have good, clear, relatively easy mathematical ways of quantifying what we're doing. It's none of the math is hard. Everybody on the shop floor can calculate that if they need to. It's very basic. In some situations it may be a little conservative. In other situations it may not apply, and that's really what we're going to get to next. So what if our real life situation is different from the parameters that were under investigation. We have a different temperature, we have some other grade. Well, let's talk about specifically about grade, about material type. So we've talked a little bit about like the 4130 that you used in your recent project, its composition, how it responds to heat treatment. What we want to understand now is how do different materials behave when you do plastic deformation at elevated temperatures, okay? So there's a variety of ways to go about gaining an understanding of this. What I'm presenting here is an older technique for gaining this information, which is called a hot twist test. This is not one that's actually very common in industry anymore. Today, most of this kind of information would be generated through using much more I'd say much more advanced research tools. There's one particular called a Gleeble machine that allows you to use very small specimens. You can do all different kinds of thermomechanical processing at different temperatures with different cooling rates, and so you can combine your deformation and forging characteristics with cooling characteristics to look at how that affects microstructures. So it's a very powerful research tool, but it's also very expensive. So we see them at some universities, you see them at some very large industry R&D centers, but they're not sort of widely available. And when you do find them, you know, like if Scott Forge wanted to take advantage of one, we could basically rent time on one, which we've done at some universities, but that's expensive to do. So you only do it in certain rare circumstances. But this information was generated, this particular data set was generated by the Timken Company and was published and made available in publications that they had out in the industry years ago because they're a supplier of steel bar to the forging industry. So this was something that they put together in support of their products for their customers. What this shows us is temperature on the lower axis, and then torque in foot-pounds. And the way the test is done is you take a 3 foot long bar, 5/8 of an inch in diameter, and you use a small furnace in the middle of the bar so that you can heat just a region in the center. The ends are left at room temperature. One end is clamped to a load cell, and one end is clamped to a motor that will rotate it. And then you just rotate that piece. The clamped end that's in the load cell is fixed so that it won't turn. And you end up twisting the bar. And that twisting action develops some shearing stresses, which are somewhat similar to the things that happen during forging. So it's not a bad test for this kind of work. So you do the test, you do it at all different sorts of temperatures, and you measure the torque. And you can see here that you get lower torque at high temperatures, higher torque at lower temperatures. That's sort of an intuitive thing. You probably figured that out by some of the forging that we've done already. When the metal's cold, it doesn't move as easily as when it's hot. But this also lets us see how different materials compare with one another. And so on the on the right-hand side there, you can see several different kinds of materials. We've got some plain carbon steels, 1015 and 1117. There's a 4140, which is very similar to the 4130 that you worked with in your little pry bar project. We've got 4340, which is a higher alloy steel, still in the low alloy steel family, similar to the 41 series, but with a nickel addition for better hardenability. And then we have 3 different stainless grades. The 410 and the 416 are what are called martensitic stainlesses. So these are stainless grades that have around, say, 14 to 16% chrome, and then some carbon, and they can be quenched and tempered just like your 4130 to get a wide range of hardnesses and strength properties. They are corrosion resistant, but they're not going to be corrosion resistant in all environments. And if you're in a very aggressive, corrosive environment, that's not going to be a great choice. You're going to want to use something more like that 304 that's up there. That's an austenitic stainless steel. That's one which does not undergo a phase transformation, so the strength available in that grade tends to be fairly low, but it's got better corrosion properties. So these are all grades that we work with at Scott Forge. They're very common in industry, and we can see how they compare with one another in terms of the amount of force needed to move them. Over here, 2300 degrees, this is a typical maximum forge temperature for a lot of things that we would work with. And we can see that at this temperature range, there is a spread in how much torque, or we could say flow stress, is required to move that, but they're fairly close together. As we decrease in temperature, we see that that spread is magnified substantially. So in the practical application of this is that not every grade is one that we can forge at this temperature. Some things, because of their composition, require that you start at a lower temperature. So you may be down here at 2200 degrees, or for certain things you might even be down here at 2100 degrees. And now we can see that there's quite a difference in the torque or flow stress required to move those different alloys. If you're down here, which is kind of where that experiment was done, you can see that some of the grades aren't even forged at such low temperatures, but if they were, they would be really difficult to move. Are there any questions on that? We're going to go to another parameter. Please ask questions.
So is 1900 like red hot, or like what color is it?
Okay, so when we're working something at work or downstairs in the lab, you're going to see that steel and iron starts to glow and have a visible color to it at about 1200 degrees in a dark environment.
Okay.
All right? If you have bright light, you're not going to see that until a few hundred degrees hotter than that. Your 1900 is actually pretty hot. It's hotter than most of your heat treatment temperatures for most things. From a forging standpoint, normally we would start, for most grades, you're going to start here at 23. You'll work at temperatures lower than this. We'll frequently work down, even to say 1600 degrees or 1700 degrees in that range. Does anybody know where these temperature ranges come from on the forging side? What would be the things that I'd be concerned about when I'm setting that up? Okay, take a wild guess. Anybody? All right, so hypothetically, what happens if I come all the way to the temperature off my graph over here somewhere? Then what happens?
Yeah.
What?
You melt your steel.
You melt your steel. So that's one boundary condition, right? Forging's not casting, so we can't melt it. Right? That's a constraint that is placed on us by the industry, right? So that's off this graph, right? And what temperature would that be?
Celsius.
All right, I'll take it. What is it in Celsius?
1200.
Okay. All right. Pure iron is going to melt between, say, around 27.5, roughly, Fahrenheit. Okay? Now, of course, we're nowhere near 2700, right? We're at 2300, so we have a cushion. Why? Why do we have a cushion? Yeah.
Avoiding it melting at grain boundaries.
We're avoiding melting at grain boundaries. That's very important because we know, as we talked about before, that you get non-uniform composition, so you can have local regions that may have substantially lower melting temperature than what your bulk chemistry would predict. That's an excellent reason. Any other reasons? Okay.
Avoid grain growth and recrystallization.
Not so much in forging. On the forging side, that's not usually a consideration for most things. There's exceptions to that, but generally not a concern for us. Anybody else? Keep going then if you...
Avoiding scale.
No, not really. You're at such high temperatures, even at 2,300 degrees, that you're going to get some pretty pretty heavy scale layers in large cross sections. Yeah.
Is it grade like other tools like your die?
Okay, that's a good thought. It's not one that is in practice something that that's really a real problem for us, but it's an excellent thought. Yeah. Nothing else?
Nope.
Okay. All right. So the grain boundary melting is probably one of the most important based on local chemical segregation. Okay. But to go along with that and related to it is when we start doing deformation, your deformation is going to cause friction. We've been talking about that for the last 2 weeks. The friction, what happens when you have friction? If I rub my hands together, they're going to get warmer, right? The same thing happens even if my metal's at 2300 degrees. If I start smashing those molecules, those atoms together, making them move back and forth against one another, they're going to get hotter. You may see this in your forging lab. If you sit there and you're forging away on something, you can actually start to cause the metal to actually increase in temperature if you're fast enough with it, right? So we have to allow for that in the forging process, so you have to have some extra cushion because you're going to get internal heating. It's called adiabatic heating from internal friction. So those are the two primary reasons. And then there's one other reason, and that has to do with the furnace, the ability of the furnace to control temperature and hold a uniform temperature. So furnaces that are used for forging are not, they're not typically as precisely controlled as those that are used for heat treatment. That doesn't mean that they can't be, but in general they're not. So the furnace, you might set your furnace at 2300 degrees and it may creep up a little bit, may go to 2325, 2350. So you need to allow for that variation in furnace temperature as well. So that's where your upper limits come from. Now, what about on the lower end? What would be driving the choice of lower end temperature? Alex, you look like you have a guess. No? No? No guesses? All right.
How much worse your machine can apply?
All right, that's a very basic one, right? How much force is available? If we know that the flow stress goes up with decreasing temperature, then at some point you're likely going to reach the limit of your equipment. So that's a very good choice, very good idea. What else? Yeah?
It'll crack if you hit it a couple times.
It could, yeah. You could get to a point where things might start to crack. Why? Yeah?
Because that graph. Okay, actually, so it's less ductile at lower temperatures.
That's right.
So if it starts approaching the ductile to brittle transition, that would definitely crack.
Well, your ductile to brittle transition is sort of way down here in the other room, so maybe not that specific quantity, but you are going to get a difference in behavior, right? So the flow stress is going to go up, and so instead of flowing, you may reach a point where the metal just can't hold itself together anymore, and it's going to tear. That could happen. That assumes you have enough power to make that happen, right? Your equipment may or may not be capable of that, but if some companies have equipment that could do that, so that's a concern. Think about it in terms of phase diagram, though. Okay, right? What do we know about the phase diagram?
Austenite is FCC, so it's a lot easier to move while it's still the austenite.
Yeah, that's right. That's right. Now, certainly 1900 is still very much austenite, right? For most of these materials, you're going to see that all the way down to, say, even 1400 degrees. It's still going to be austenite, but the flow stress is going to continue to go up and up and up, and you may run the risk of having a tear. You're also going to have a thing called dynamic recrystallization. When you deform the metal, you're going to put in a whole bunch of strain, and you're going to break those grains we talked about in the first lecture, where you've got these as cast grains, which you're trying to break up, and you break them up, but then they nucleate again. You're nucleating new grains during forging, not because you're going through a phase transformation, but because you've put in a bunch of plastic deformation, which is stored energy, strain energy, but you've done presumably a lot in one push, and now there's enough energy that it's going to trigger a recrystallization, also because you're at high temperature. As you get to lower and lower temperatures, that's not going to happen as fast. So you're going to have other issues. So your forging window is kind of set by not melting on the one end and staying within the austenite phase field, but also being in a range where you can get dynamic recrystallization happening, because if that's not happening, then you're going to just build up more and more strain in the part, and eventually it's going to want to tear apart and rip. So that's kind of where we're at, where our boundaries come from. There's also the sort of the non-physical metallurgy parameter of, at low temperatures, it's harder to move the metal, it's less efficient. So you just don't want to waste a lot of time either, right? So there's multiple different contributors there. Okay, so this is our graph of temperature versus flow stress or torque as it's presented here. Any other questions? Any other answers to my questions? All right, so we're going to show another graph. So this is the other parameter that is measured from this test, which is the number of twists to failure. So it's the same exact situation. Pick a temperature, heat your metal piece up, twist it until it rips in half, and count the number of twists. And then do that over a variety of different temperatures, and we can see what happens. And we have on the high end, upper temperature range, more twists to failure, low temperature range, fewer twists to failure, which gets to our kind of where does our lower limit tend to come from, which was the tearing that I was talking about, right? So
Is that a square piece or what is
this is a round. This is a 5/8 inch round bar that is fixed on one end. A little furnace is placed over the middle section of it, and then the other end is gripped by a motor, and it's twisted at various temperatures, and they measure torque, and they measure number of twists to failure. So we see that in general, higher temperature, you can do more twists before the metal's going to rupture or going to fail, right? So that is consistent with what we were just talking about. But I want to draw your attention to a couple of things. We have this alloy here, this dark purple. We get to this spot, and then all of a sudden, it starts to drop off. We've got one here that drops off at a little different temperature. Anybody have a guess as to why this one has this drop off at this point, whereas everything else is, out here before you start to see that? Look at the grade names here. That should give you a clue. Yes.
hard to see which one's
What are the other grade names?
Okay. Perhaps I assumed some knowledge you guys don't have.
Which one's which here?
Okay, so this one here, this dark purple, is this one here, 52100. This light pink is 1015. This blue here is T410. The yellow, 1117. You've got kind of a navy blue or a darker blue down here. That one's T416. So to your question, what do the names mean? Has anybody learned about steel naming and how we talk about steel? Have you guys learned that a little bit? Okay, perhaps this is a good time to review then. I assumed you were already familiar with that, but maybe I shouldn't have. So let's just start with those names up here that are 4 digits or 5 digits, just those, right? These come from the SAE, Society of Automotive Engineers, and it's an old system that we've used here in the United States for a very long time. Anything that starts with a 1 is considered a plain carbon steel. That means that it's got iron, carbon, and perhaps a little bit of manganese, and that's all that's in it for alloying. Now you have some subgroups. I show here 1015 and 1117. Those are both plain carbon steels. The 11 indicates that we have added some sulfur in. The sulfur is not present for any benefit to hardness or mechanical properties or hardenability. It's been added to make the parts easier to machine. We have the other thing here then, the 15 and the 17 give you the amount of carbon as weight percent, right? So in this case, it's 0.15 carbon or 0.17 carbon. In the case of the 52100, the 100, this is 1% carbon. Sometimes people would call these points 0.01% being 1 point, so this would be 100 points of carbon. Your 4140, 4340, those are 40-point carbon steels. Now, these three here, the 5200, 4130, and 4340, those are considered low alloy steels. They have alloying elements in them in addition to just carbon and manganese. The particular alloying elements that are there are indicated by the 4 and the 1, or in this case, the 4 and the 3. And there's a whole series of these. I've only got a few of them up here, but you could look up, you can get a whole list of these online or in any of the reference books of all different kinds of steels. These are ones that we commonly work with at Scott Forge. They're very common in industry. So a 4140 is a steel that has about 1% chrome and about 0.25% molybdenum. And then 40 points of carbon. 4130, very similar, it's got the same chrome or similar molybdenum, a little bit less carbon. Your 4340 is got chrome and molybdenum, just like the 41 grades, but then it has an additional alloying element, nickel, and the nickel in this case is in the range of about maybe 0.16 to almost 2% is typically where that nickel falls. That nickel makes this grade much higher in hardenability than this grade. And we'll talk about what that means more in another lecture, yeah.
Like knowing all the different compositions as far as like what the other alloying elements are and such like that, that's just through experience that you know what composition is that, right?
It's from working with it, but when I started my job at Scott Forge, one of my colleagues printed out a list of all of the grades that we worked with and their compositions, and I took it home and studied it. And I don't remember all of them. I never managed to memorize them all because there were about 1,000 in that book. But the ones that I work with all the time are the ones that I know off the top of my head. And it'll become the same way for you guys in whatever industries you go into. You'll become familiar with those materials that you're working with on a daily basis. 52100 is a chrome, and it's pretty much just chrome, around 1.5% chrome, but then it's got 100 points of carbon in it. Now these others, we've got these T, the ones that start with T, those three are all stainless grades. So stainless is going to have much, much higher alloying. You're typically going to see chrome levels in the at least 12% minimum, 14, 16, 18, 20% depending on the alloy. The 400, the 410, and the 416 are primarily just chrome as their main alloying element, and then a little bit of carbon, and that's about it. The 416 has some sulfur added back to it to make it easier to machine. The 304, T304 and T316, and there's 327 and 321 and 321 and 347. Those are all what are called austenitic grades. So they have more chrome and they have the additional element of nickel, but the nickel is now in the, say, 8% range or maybe more. That 8% nickel stabilizes austenite all the way down to sub-zero temperatures, which is great because you've got something that will maintain ductility. So if you're going to be dealing with liquefied gases, those are really cold, so austenitic stainlesses are used for those containers. And if you need something that's got very good corrosion resistance, these grades are ones that you go to for that because that nickel enhances corrosion resistance as well. So they're really commonly used for that. But you could see if I have 304 with say 14 or 16% or 18% even chrome and 8% nickel, that 316 would be like an 18.8 chrome nickel. Now you're talking about having what, probably close to 25% of the composition is not iron. It's chrome, nickel, and you might even have a few other things in there. So those are very highly alloyed steels, and you can see that the way they behave when you go to do plastic deformation is much different here than if you're dealing with a plain carbon steel or even one that's an alloy steel but a low alloy steel, right? That extra highly alloyed nature really changes its behavior when you go to do plastic deformation.
Would it be helpful if they looked at the phase diagram for the purple one?
For This one? Well, it would, but I would think that you'd all have that memorized by now.
High carbon content has a lower melting.
That's it. That's exactly right. The high carbon lowers the melting temperature, so everything that we do from a processing standpoint has to be shifted this way on our graph so that we don't run the risk of melting it. And that's what you see here, is that when they did this work, they've started to get grain boundary melting, and so they were getting, this specimen was failing, it was actually ripping apart at a lower temperature than something with a lower carbon content. Yeah, excellent. That's exactly right. There's one other thing that I want to point out here, which is this difference between this pink one and this yellow one here. The pink is 1015, so plain carbon steel, 15 points of carbon, and this is 416, which is a martensitic stainless steel. Not really any more carbon though. Okay, and I'm going to jump back to the other graph for just a minute so you can see that on this graph, these two are pretty similar. They're not identical, but they're similar, right? Well, that was the torque versus temperature. But now when we move here, we see that the amount of work, number of twists to fracture, is dramatically different between those two materials.
So the yellow one is which one? It's 117?
Oh, excuse me, it is. Yep, I totally misspoke. It's 1117. Thank you for pointing that out. I have two resulfurized materials on this graph, and the other one got it confused. Yes, so these two are nearly identical in composition, except that this one has extra sulfur in it, which my machinist friends really like. But why would we see such a difference? The amount of force needed to move the two materials is nearly the same. That's what the other graph shows. But the amount of work I can do before failure is dramatically different. Any thoughts about that?
Where is sulfur combined with?
I know the answer.
Why do you add, I don't know, manganese?
Right. So you put manganese in steel to combine with sulfur. We do that on purpose because if you had free sulfur, it makes the steel very difficult to do any kind of plastic deformation, forging or rolling. The steel tends to crumble. Years and years ago, it was hard to get sulfur out of liquid steel as the steel industry was developing. They found that they could put manganese in and they could deal with the sulfur that they were having a hard time getting out. And so then you had material that you could use. You could forge it and roll it, whatever you want to do with it. It was fine. Today we can get the sulfur out of steel. Steel making technology is advanced, so we can do that, but there are some good reasons to keep a little bit of sulfur in steel. It helps with certain things. But in this case, we're talking about having more than that amount present. This sulfur has been added back at a much higher level to make the steel easier to machine. What's happening is you're still forming manganese sulfides. In fact, in these grades, they actually boost the manganese as well to make sure you've got plenty of manganese sulfides. And when you now have an object that you're taking to a machine shop and it's made from one of these materials and they go to start cutting on it, all these little sulfides act as chip breakers, so that when they start to generate a chip, a machining chip, it breaks off into a nice small little chip, which is great because then it doesn't get wrapped around the chuck. It doesn't get it can cause real long stringers, which can be really hazardous. So it allows the machine shops to be more efficient with their machining setups, use faster speeds and feeds. So it's great if you're doing a lot of machining. But manganese sulfides are not steel. They're much softer, much weaker. So if you have a high concentration of manganese sulfides and you're doing some plastic deformation, that's going to potentially serve as an initiation site for a rupture during the deformation process. And that's what's being shown here, that those sulfides that's what's happening. And we observe this at work. When we forge these grades, we have to use extra care, because if we don't, we'll actually cause internal tears and ruptures in the resulfurized materials that we wouldn't expect if we were just looking at the carbon and alloy content of this grade, you'd say, well, that's just like the same as 1015 or 1018. That's like about the easiest thing in the world to work with, right? That's this. But the sulfur completely changes what we have to do to protect the integrity of the part. That's a different part of our lecture than the cogging, but I wanted to illustrate how different materials behave in different ways, and why, as a forging company or forging operators, we have to understand that, and we've got to know in real time what to do, because at where I work, we'll forge one thing and then another thing and then another thing and another thing, and so every 5 minutes or whatever it is that you could be bringing a different alloy to the press, making a different part. And so you as a forging person, as an operator, have to know what it is you're dealing with and tailor your forge technique to be matched with the material you're working with. Things that you can do with this grade, you can't do with this grade. Minimum forging temperatures on something like this are going to be kept hotter because it's going to be so much more sensitive to that tearing than you would on this grade. So that's something that the operators have to really have a great sensitivity for. All right. So, questions on that before we move forward?
So essentially, the manganese sulfides act like dirty steel. Acts like there's
Yeah, right. I mean, yeah, I mean, from the experience that I think you've had, Dr. Metzloff, and I've had, it would be almost like the challenge you have in forging a piece of wrought iron, right? It's not quite that bad, but it's similar to that, right? So the takeaways from those two graphs, getting back to how does this apply to what we're doing when we're cogging and we're trying to close up the holes in the ingots. First, as our alloy content increases, so does the amount of force required to move the metal. Yeah?
So wrought iron has high sulfur content because it's old, but smiths like it. So why would they like it if it's much harder to forge?
well,
It depends on the smith. Some of them like it, some of them hate it. It does have sulfur in it, but what it also has, and why it behaves in the way that it does, is it has iron silicate in it. And so wrought iron is, from a metallurgy standpoint, wrought iron, I think, is best described as being a composite of iron and iron silicate. And the iron silicate, the iron component is generally extremely low in carbon and alloy content. So that means you can be on the extreme end of the temperature range. You can forge wrought iron at much higher temperatures than any of the things that I showed here. That's nice because it's soft. The iron silicate actually starts to melt at a lower temperature than the iron. So if you're at that temperature range, it's actually really easy to deform. The trade-off is that you have to stay at that temperature range or the iron silicate starts to solidify, and now it's not easy to deform, and then it wants to crack and crumble and be difficult to work with. Wrought iron was available in different grades that sort of were based on how much iron silicate was in them, and so the lower iron silicate versions were easier to work with. You had a wider window. Also, because of the way wrought iron was produced, it was very sensitive to sulfur and other phosphorus, other impurities that were in the fuel sources that were used to heat it. So wrought iron from certain parts of the world was recognized as being superior for certain applications that required a lot of deformation. So you see a lot in ornamental ironwork in particular, where there was a lot of cold bending or sheet metal work, that they preferred iron from Norway and Sweden because it was very clean and you could do a lot with it. If you're making something like the wheel rims for a wagon, you don't really care so much about that, and you can use a lower grade of wrought iron. So today, if a blacksmith is working with wrought iron, it's wagon tires are a source for wrought iron, but they're notoriously difficult to work with. You've got to keep them very, very hot. So people like it today because they like to recreate history. Some folks are specializing in restoration work of period pieces, so they want to use like materials. Some people just like it because they can forge something out of it and they can etch it and it'll show the grain flow. I've showed some pictures of that already. So there's some reasons to be attracted to it. It's pretty neat, but it has this quirk of some challenge. The one other thing is that if you're doing a lot of forge welding, which was very common, and because before you had electric welding, everything was put together by forge welding processes, and I showed that in our first video, or our first lecture. Wrought iron with all that iron silicate, because it melts at a lower temperature than the iron, it actually is self-fluxing, so that you can take these two pieces that are at, say, 2,500 degrees, the iron component's still solid, but you've now got a liquid layer of iron silicate, which is protecting the iron from oxidizing. So then if you design your joint properly, you bring the two pieces together, you start to hit them, the liquid iron silicate is forced out of the joint, and you've got two clean pieces of iron that come together, and then they'll make that bond that we talked about. So they like it for that as well.
Cool.
All right, so as the alloy content increases, the amount of force required goes up. As temperature decreases, the amount of force required goes up. These are all fairly intuitive. And also, as the size increases, the amount of force required goes up. So these are all practical considerations that we have to think about when we're forging large ingots that we want to close we want to close up those holes. Different materials are going to behave in different ways. Different sizes will obviously require more tonnage, and the material type is going to determine the temperature that I can use, and of course if I'm at a lower temperature, I'm going to have more force required. Now, do those three things make sense? Right? Okay. So, from a forging standpoint, if we know that those three things are all going to require increased tonnage, increased force to make the metal move, there may be a tendency to want to change a parameter or two or three to try to make my job easier. Right? Now, I might be tempted to turn up my furnace temperature, but I run the risk of melting the parts if I do that, so I can't do that. I may not have the luxury of using a smaller cross-section because the customer's ordered a part that is a big part, so I have to use a big starting cross-section. But maybe I can have less metal underneath the die so that it doesn't require as much force to deform that die bite, right? If I have a full die bite, then it's going to take, the maximum, whatever it is, to move that volume of metal. But if I decrease the volume of metal that I'm working with, then of course the amount of force needed goes down. That's not bad, maybe. But it could be. It could be. Why could it be? Think about yeah.
It's a lot more time consuming.
Well, it's more time consuming, sure, yeah. So there's an efficiency component there, yes, okay. You have to make more strokes to get down the length of the part, okay, that's one. What else? Think about the little bit of math that we did earlier in the lecture. Let's go back to the illustration that I gave. If I have a 10-inch cross-section and I have a 30-inch die bite, how much metal am I deforming at the center, assuming I'm able to get the 20% draft? It's 1/3 of my die bite, right? So about 3.3 inches. Well, so now I'm going to shorten my die bite. Let's say I shorten that to 5. Well, I'm going to shorten up whatever that L dimension is going to get smaller, right? And at some point, I'm going to reach a spot where the amount of metal underneath the die is not enough to get any work happening at the center line, right? So I might be moving the metal on the outside, and I may see deformation happening, but I'm not actually getting deformation happening at the center where the holes are that I'm trying to close up. I've seen this happen on numerous occasions, and that's what my show and tell piece today shows. So you can take a part and you can forge it from its starting ingot size down to some target dimension and get it all the way there, and you can have a large reduction in area. So I said earlier that you need a minimum of 3 to 1, but you can have 6 or 7 or 8 to 1 and still not work the center line if you're not hitting those targets that we talked about earlier. And I've seen that happen. So there's that temptation on the part of an operator to shorten up the die bite so that they can get deformation to happen, and they're thinking that they're accomplishing the goal of moving the metal and getting things done, but they're actually not, because the die bite's too short, and now they're no longer working the center line, right? So that's one circumstance that's actually something we have to work really hard to avoid, right? Hypothetically, what if we take our W over H to a very minimal kind of an extreme? I'm going to show a sketch here. This is what we get. If we imagine here we have our little friction pyramids. You can see these things are super short, and so to get them to collide with one another, I have to do an enormous amount of deformation, right? I have to really have a very deep draft before this and this are going to collide at the center, right? But if I've got a die that's only this wide, I can't do that, right? I can come down a certain amount, but eventually I'll come down, I'll end up with a sharp corner, and if I try to make another bite, I'll cause a quality problem. I'll cause a lap. Let me draw that on the board over here. So if I have some cross section like this, and I bring a tool down and I make a real sharp transition and I make it really deep, like this, right? Now, when I bring, if this is my die up here and my other die down here, if I make this kind of a push, this corner right here, there's nothing supporting it. So it's going to move out in this direction, like this. And when I get done, I'll have something that's this dimension. So now we've completed this forging. But because this metal has laid over on itself, there's actually going to be a crack right here. Right? And I probably would see a corresponding one here also. Right? So these are called laps. Put that up here. A lap. This is where the metal has folded over on itself. And we avoid this by making sure that we don't do this. We keep our tools with some radius here, so that when you forge this, you get a radius in this corner. And we also limit how far we come down, so that we're not pushing to the point where we're up here way past this radius, right? So that's going to limit how deep a draft we can take, because we don't want to create this quality problem here, right? So there's another limiting factor. So when we're forging a big cross section, we may have every intention of meeting the W over H equals 1/2 the cross section, and our draft is 20%. So we may have every intention of doing that, but we can't without, if we did that, we would cause a lap, right? So we can't have that happening. So in that circumstance, we have to use a shallower draft, recognize that we're not going to be working the center line of the cross section for that part of the forging process, and make extra passes with deeper drafts as we are able to get to the end result that we want. But if we never make that if we always keep a shallow draft to prevent a lap, or keep a narrow die bite because the stock is so stiff that we can't move it otherwise, then we're never going to work the center line. So we have to figure out the balance in there. We may have situations where we have to start off that way so that we don't cause these laps, and that's okay, but then we have to just allow enough additional deformation so that we get the deformation at the center line that we need. So it has to be planned out. We can't be haphazard in what we're doing. Back to this little sketch here, we use a technique like this to actually cut metal, where we take a tool that is about 2 inches wide, and we'll set it up on top of the metal, and we'll use the press to push it right on through. And we'll push it through most of the way, and then we flip it over 180 degrees and push it back to the other side, and we can very quickly separate pieces into smaller chunks. That's actually about the fastest way there is to cut a piece of steel. But it illustrates the fact that a narrow die bite taken to extremes is never going to allow you to work the center until you're within just the very smallest amount of the center, and at that point you're not going to have a forging of any significant size. So we have to balance our die bites and the deformation that we're trying to do with working the center line. To give maybe a more specific example, if I had, for example, let's say an ingot that was 50 inches in diameter, maybe let's say a 60-inch diameter ingot, because these we work with fairly often, that weighs about 80,000 pounds. And I want to forge that down and make, maybe I want to make a shaft forging with a 20-inch diameter head. So I bring that to a 3,000-ton press. Now, I wouldn't ever do this at Scott Forge because we have other equipment, but just for the sake of our example, I can get that metal hot, I can bring it to the press, I can deform the metal with the press. But the ingot is 50 inches in diameter. My dies are, say, 30 inches wide. So excuse me, I said it was 60-inch diameter. So if my ingot is twice the ingot cross section is twice what my dies are, so I'd be right on that. W die width is 1/2 of cross section, so that part's met. That's fine. But now, if I'm going to do 20% deformation, maybe I don't have the power to do 20% deformation with a 30-inch die bite. So maybe I have to back off on my die bite and make my die bite, say, 15 inches. Well, now I can do the deformation, but the die bite is much less than 1/2 the stock cross section, so now I'm not going to be working the center line of that ingot. That could be okay. I can work that ingot down to some smaller size, say 40-inch cross section, and I'm just making up numbers here, so if we actually plugged it into the math, you might find that they don't actually work out quite right. But I'm just trying to illustrate a concept. If I get it down to a 40-inch cross section, and now I can have that 40-inch cross section at the maximum forging temperature, bring it to the press, use a 30-inch die bite. Now my die bite is actually more than half the stock cross section, so that's good, that's helping me out. And if I can get a 20% draft, which I may be able to do at 40-inch cross section that I couldn't get at 60-inch cross section, now I'm working the center. So the setup is to figure out where in the process I'm going to start meeting that requirement that we showed, where W is 1/2 of H, and I've got 20% of draft. At that point, wherever that is in the process where that starts to happen, that's when I can start having confidence that I'm working the center line. And any work done prior to that point may be useful and even necessary to get the starting piece knocked down to a smaller size, but it's not helpful in getting the porosity closed up. So I have to know when in the process I'm going to start closing the porosity, and then how much additional work I have to do to close that up effectively so that I don't have porosity left in the final part. Questions on that?
That'll be important when we're closing up that ingot there.
It's going to be very important. Yes.
Now, the dies, we're actually designing the dies, so this is really timely.
Okay.
We're going to make new sets of dies. And the ones that are on there now are 4 inches square. And it's a 3-inch section, so we could, if we have it force, we could actually, you know, pretty easily, we don't have a bottom 4-inch one, so we have to make that down.
Yep.
And we might do that initially,
Uh-huh.
but I think we might make that 2x4.
Sure.
We're trying to figure out what radius to put on it and that kind of thing.
Right.
so
Sure.
about that.
So that's probably something that maybe could be a good discussion topic while you guys are in lab tonight, in between the forging project that we're going to be doing. Any further questions on that? No? Okay. So I've got here just a series of slides of showing, this is a large copper, yeah, I think this is a copper ingot. This is a, yeah, so this is actually this is a nickel aluminum bronze. The grade number is C63200 if anybody wanted to go look it up. It's extremely corrosion resistant copper alloy that the Navy uses quite extensively because it's really good at avoiding marine growth that likes to get on things. So
Also, resistant to what we call the water jets.
cavitation.
Cavitation.
Yes, yeah. So it,
Cavitation corrosion.
Yep. So it gets used for things like large bearings, propellers, things. We're not forging, propeller would be that, right? Yeah, we're not forging those, but we do forge the large bearings out of it. So this just shows you some pictures of breaking down a pretty large cross section, and I think this one is a 50 or 60 inch diameter cross section. So you can see here where you have the original cross section being held by a manipulator. You can see we've got it taken down to an intermediate size. One thing I'll point out in the previous image, you can see that this particular ingot has a fluted surface, and that's done to help minimize the amount of segregation that happens during the solidification process. And those flutes, you can kind of see a remnant of them here. These stripes are where the flutes left over from those flutes. And then the next image, you can see that cutting operation I described. This cutting tool is only 2 or 3 inches wide, and so you're not really getting any deformation to the center. You're just cutting through the work. So that's sort of that ultra extreme narrow die bite. It illustrates what's happening there. And you can see here finishing that cut, and then we get a little bit of a flare, and so they flatten that out before they move on to the next step. Questions on that? Okay. I want to go a little further, but I don't want to take too much time away from lab tonight either. But this section here is going to be very, very helpful for your lab project tonight. So we talked about if we have the W over H dimension is perfect, so W over H is at least 1/2, but our draft is too small. So we haven't touched on that yet, right? We talked about what happens if our die bites are too small, but what if our die bites are just fine and our draft is too small? What do you think will happen? So in both cases, we're not going to work the center. But why? What's going to actually happen? What shape do you think the metal will take on if we have a shallow draft? Any guesses? Yeah?
So this draft is minimized to mean that you have like a sharp transition? Like it's a
Well,
sharp point, or does that mean it's very flat?
it just means that instead of pushing, so if I had in my example earlier of a 10-inch square and I pushed in 2 inches, 1 inch on each side, that'd be 20%, right? So I'm saying now, instead of pushing in 20%, what if I'm only pushing in 5%?
Okay.
Or
Not
2%.
like a casting design draft at all.
Right, no, so okay, yeah, in casting you're talking about the relief angles to get a pattern out of the mold.
Okay.
Right, that's not what draft means in this case. This is the distance the dies penetrate into the work. Yeah. So what would happen if that was really shallow, do you think? Any guesses? No guesses at all? Oh? Yeah,
You're
Evan?
saying, like, your cogging it and then you rotate it and continue again, because if you don't have a long enough draft, you wouldn't close the center and then just reopen the center each time.
Well, that's true, yeah, right? If you never had enough draft to ever deform the center, yeah, the center's just going to kind of be there and not be really worked at all. Even though the cross-section continues to get smaller, you're theoretically never going to really deform that center line. Yep. But what would the shape be, do you think? Let's just assume, make it easy, assume just one pass down a square cross-section with a draft that's on the, too shallow, not deep enough. What kind of shape do you think you'd end up with after that? No guesses? No guesses? Okay. So it would look like this. The metal, if you have a shallow draft, you're going to move metal, but it's only going to be the metal that's just right here, and up, of course, on the opposite side as well. So you end up with a shape that's kind of a dog bone shape. So if I have this dog bone shape, and I continue to make passes on these same two sides, what will happen? It'll get a lap. Yep, it'll get a lap, right? What'll happen, this metal here and this here will continue to get closer together, but the center is not ever going to really move out. So these two will kind of run into one another and you'll have a crack right here, right? So I wanted to get to this point because the project tonight is starting with some rectangular section material. And we're going to be forging that down into a handle for, do we have to use special terms to talk about what we're making tonight, Dr. Metzloff?
It's a letter open as long as it comes out of here as a unsharpened device.
Unsharpened device. This is creating the handle section of this tool. So we're going to start with a rectangular cross section and forge that down, and eventually will become square. But there's going to be a tendency for this shape to develop while you're forging, especially if you don't have a very heavy draft, or in lab terms, don't hit the metal very hard, right? So to counteract that, what you have to do is you make a blow that causes this to happen, but then you lay the metal flat 90 degrees and you flatten that back out so that you don't create that crack or seam down the center. So you work a little bit and then you lay it down and you work a little bit. Now, in our lab project tonight, we are not trying to consolidate an ingot. We have a thin little flat bar. We're not worried about that closure of shrinkage cavities or any of that stuff. That's all been taken care of. Right? So right now, what we're talking about is just how do we control the shape of the metal to get the outcome that we want. And so in this case, we still have to understand these concepts of die bite and draft and force and temperature management. All of that's important to us, but we don't have to worry about trying to close up holes. So we're going to start with a rectangle. We're going to stand it up on edge. We're going to forge that down until we get close to a square. And in doing that, we'll have to go back and forth so that we don't make these cracks along the edges.
If you hit it harder, what is it going to look like?
So if you hit it hard enough, what will happen is you won't get this going on. It'll become more of a barrel shape, right? And that's ideal, but that may not be feasible for everybody, and that's okay. Right? We all have our own abilities. Some of you have done some forging, have more practice at it than others. Some of you are bigger and stronger, can handle bigger hammers than others. So that's fine. Everybody's going to have their own way of doing it. What you probably will find is that by working in teams and using some sledgehammers, you'll be able to make a lot of progress pretty rapidly on this part of the job.
Is it similar to when you're using closed die forging, when you're using a hammer? Just work in
Yeah.
taking lighter blows.
Yep.
But then in a press forge where it happens all in 3 passes, you tend to bulge out in the middle.
Right. That's part Similar, yes. A hammer will work the metal all the way through if it's big enough. But you're limited to how big a hammer you can get, the surface area you're trying to deform, the shape. Especially in closed die work, you've got often metal that you're trying to force from one area of a die into another area of a die. So you've got limited cross section, and you're trying to make metal go through that passageway. So it's not. It's not as easy as having a simple shape that you're just bringing together two dies and metal's got freedom to flow on both sides and so on. So it's similar but not the same. But if you have a big enough hammer, you can work the metal all the way through the center just like you can with a press. You might remember I put a slide up that showed the relationship between hammers and presses in the very first lecture. And I said that from an industrial standpoint, doing this kind of open die type of work, that you need a hammer of about 50 pounds falling weight for every 1 square inch of cross section that you're dealing with. And then there was a slide that related hammer size to press size, and I think that we had there that was like, I think it was something like an 80,000 pound falling weight hammer was equal to around a 2,000 or 3,000 ton press. So what you're seeing is that you have to get some truly enormous hammers to begin to have something comparable to the kind of presses that are used even on what would be considered sort of medium size in the open die forging industry. So that's probably a good place to stop right now.
The homework deals with ingot. We can kind of do some I'll send those questions out. Try to have it done by next week. And then we're going to forge that, I think, we'll have to be 2 weeks from now, we'll have to forge it. I might just do the calculations and get the students working on it, so we can bring it over here and roll it. I don't know if I want to do an operation. Any questions?
Questions? So this section has another maybe 20 or 30 slides in it because we haven't really covered yet the techniques that we use when we're dealing with small cross-section forging, which is fine because we kind of spent a lot of time on how do we deal with ingots, and then what you do when you're dealing with small cross-sections is kind of the exact opposite. So to have them in different lectures actually works out fine.
And then maybe we can do a quick experiment in the lab and see if we can make the bulge versus the
Sure.
double bulge.
Absolutely. Yeah, absolutely. Okay. Oh, one other thing that I wanted to, so before you head downstairs, I've got a couple of show and tell items. We talked last week or 2 weeks ago about dendrites and solidification structures. So I have this is the ingate off of an ingot, a large ingot at work that was broken off, and you can see the as-cast structure here really well. Not quite as large as the one that Dr. Metzloff has, but it still shows you what we're dealing with. And if you look carefully, you can actually see where some of these dendrites have actually grown out into free space. The other thing I brought here is a block. This is from a 400 series stainless steel, and we've got a whole bunch of holes in it. So this illustrates a really severe condition of what can happen when you don't do your forging properly. And in this particular case, specifically what they did was they took an ingot, they did a little bit of upsetting to it, but nothing like the 50% upset that we talked about 2 weeks ago as being the minimum that you need to close up holes. So they did like maybe 25% or something, a real minimal amount. And then they took and forged that shape into about a 26-inch diameter cylinder. And in combination, between the two different forging steps, they had a little bit more than 3-to-1 reduction on paper. But because they didn't actually do the things that we talked about today, they didn't close up the holes that were in the ingot, so they're all left here. And when we went and did an ultrasonic test on this forging, it failed, and we cut it open, and it looked like I'd gotten a hold of a piece of Swiss cheese. So please come up and look at this. There's one other thing that I brought. This is a forging demo. This is from a piece of material that I forged at home, but I want to show you this because it's going to pertain to your lab tonight. This shows you how metal will move in different ways depending on your die bite size. So again, in this case, I'm not trying to close up holes. I had something that was already fully closed up. It was just a piece of bar stock. But what I did was on this end, I just put the full width of the die and just hit it. On this side, I took a very narrow die bite and fed the work in small increments. And you can see that I've got much more lengthening of the stock and much less spread to the sides than here. So when we're forging tonight, where we're forging, we're going to be doing a lot of lengthening of our section using this smaller die bites at the right point, or in combination with the flattening so that we don't get the seams that we just talked about, is going to be helpful to efficiently completing the project.
And regular blacksmithing, when you use the curved one, it's called fullering, right?
Yep.
Where you purposely are trying to make the part longer.
Yes, yeah, you can use curved surfaces. So I did this all with flat tools, and it's got a little bit of a bend because it was probably a little cold on one side, or the dies aren't exactly parallel. But yeah, what Dr. Metzloff talking about is you can accomplish the same thing using contoured tools. So the horn of the anvil is a great example of that, or sometimes you can have tools that'll fit the hardy hole. If you have an anvil with a hardy hole that have radiuses on them, they're called fullers, and they're used exactly for that. Or even some of the hammers that we have downstairs have cross pins that are used to preferentially move the metal in one direction or over the other. So there's a lot of different ways to accomplish that. This is an illustration just using flat tooling.
Okay. Ready to go? Awesome.
Yeah.
So I filled the tanks. Billy, is your tank the gray one? Yes. Okay. I've replaced it with a brand new tank. So it was almost out of date. So you have a 2018 tank, so it's good for another 5 years or something like that. And then we'll just keep filling those ones.
Would be to forge out this part that becomes the handle. And the length that you need for that is kind of a function of how big a handle you want to have. I did one last night, which I left on my dining room table this morning, where I used about 11.5 inches. And I found that for my hand, that was a little longer than I needed. I could have gotten away with, maybe 10.5 or something like that. You've got some flexibility with this design because you can get an increase in length. If you go, oh, this is too short, you can always flatten this dimension down a little bit and you get a little bit more length. So you can kind of guess that. But I've got a few of them over here that are different sizes. So what we're going to start with though is drawing that out. And because we're dealing with a rectangular section, that's why I've spent some time at the very end of our lecture talking about how this metal is going to move. So I'll show you the basics of how to do that. I'll do it on my own, but I think that you'll probably find that it'll be most efficient if you work in teams. If you've got somebody who's comfortable swinging either a sledgehammer or just two hands on a smaller hammer, what you'll find is that it may not stay square. You may not get it to bulge down the middle. It may bulge on the edges like we talked about. When that happens, you just lay it down and you bring it back to a uniform thickness. You don't want to make it, thinner. You want to keep, your goal is to get this to something close to square, because then it'll be most efficient to draw out and get whatever additional length you might need. I'll start the demo, and I'm going to spend some time talking about this area right here. All of the pieces have this little notch. That's there on purpose. This is to show you where to start the transition between the blade and the handle. So you've got 2.5 inches that will become the blade. This amount of metal can be stretched out and give you a blade about 4 inches long. We're going to forge this handle section out first, but we're not going to actually bend it over and make the handle until later. We're just going to do the elongating first. The blade end, they're all a little bit radiused, and I did that because if I were to take a square section and forge it to a point, which I can do, what we find is that if you're not familiar with how to do that, you'll end up having these two corners actually come together and make a crack at the tip. So by knocking off the corners, it tends to reduce the tendency for that to happen. Some of them are, have an end that's radius not from grinding, but actually from forging process, because I forge this out of 1-inch round, so the very ends naturally bulge out, and that's a perfect shape to go into making a point for a knife.
It's 5160.
Yes.
So 5160, what is that? You might not know what 51 is, but what is the 60? 0.6% carbon, so it is hardenable. And 51, sometimes the higher the number, that they're more hardenable, but not always.
Yeah, 5160's got some chrome in it. I'm not sure what else. I don't work with it a lot.
Yeah.
It's not a grade that we forge at work very much, but it's most commonly used for leaf springs in automobile applications. So it's really easy to get a hold of. The material that I have happened to be supplied as 1-inch round bar, but you can salvage leaf springs if you want to make something out of it. Get some from a junkyard, whatever. It's pretty cheap. So let's go ahead and get started. What I'm going to do, and I'll show you I'll talk about it as we go along. But I'm going to be I'm going to be paying attention to the amount of metal I have under my hammer, so the die bite, and how hard I hit it, and draft, just like we talked about in class. I'm not going to set this entire length over the anvil and start hitting it all at once. I'm going to work a little bit on the end, and then I'm going to feed in a little bit, and then a little bit more, and a little bit more. This notch is on the side of the knife that will become the edge. So, because I want my handle to be in the same plane as the back of the knife, we need to keep that in mind. At a certain point, when I will start on the end here, and I'll work my way back here. And at a certain point, I'll get to where I'm actually going to take the notch, and I'll catch it right on the edge of the anvil, and I will use a blow from the hammer that covers the back, so that this is kind of in the middle over the hammer. The idea being that I can push this metal back this way without making a big dent here. I'll show you. It'll be a little easier to understand when we get to that point. Some other information. This is not very thick material, so it's going to heat up pretty quickly, especially once our furnaces are up to their operating temperature. It's also going to oxidize pretty rapidly, especially as it gets thinner. So you'll want to be very quick with your heats. You don't want to stop and get to talking with somebody or asking me questions while you have metal in the furnace. If you're going to do that, you need to take a break, just pull it out, set it aside, let somebody else have a turn. Because if you don't, you'll run the risk of having too much oxidation happen, and you'll end up with a really small little sliver left at the end. We'll see how the evening goes. We may take 2 labs to complete this project. I did one last night at home. It took me about an hour and a half. So you figure it's probably going to take all of you twice that long, maybe longer. So we'll just see how much energy everybody has and how the evening goes. I'm not opposed to taking 2 nights to do it if we need to. Any questions? Okay. I'm going to work right there, and what I'll do, I will turn this anvil this way so that everybody can see. This one here, I'm going to just flip around because we've got the blade side in, and of course we're starting on the anvil side. So we'll put that in so it's ready to go. Actually, here we go. So, notch is here. We're going to start. I'm going to just, for myself, just for me, I'm going to start right there, just to make it really clear where that transition's at. Now, I'm going to. Not exactly flat. of a pucker right there. That's kind of what I was talking about in class. So to fix that, and it's only on one side in this case, but it could happen on both sides at the same time. To fix that, I'm just going to lay it flat and hit it. Now, it's too cold. I don't need to work it anymore. I won't get any benefit, so I'm going to reheat it.
How dangerous is it to pound on this cold and this animal? Not too bad.
At that temperature, not too bad. If you were to let it continue to cool, you know, it might crack. Yeah. You can do a little bit of work at low temperatures, you know, where you're just, you know, just started to lose color. You could do a little bending or tweaking. It'd be okay. Now, I started, when I did this, I started with my notch down, and I kept the notch down. You don't have to do that. You can, when you get to the point of kind of defining that notch with the anvil, you do want it down. But you'll see that I'll work back and forth. I'll flip the piece over. What's really kind of neat about doing an offset like this is as long as I leave the last little bit of work to do in that shoulder area to the very end, I can push the metal back and forth from one side to the other and still get it to end up where I want when I'm all done. So the end is hot enough to work. So now I flipped it over. It doesn't make any difference really. So you can see here, this is all, you know, about a third thicker than it was. I don't want it to be that thick. I want to keep a thickness close to what I have. So now I'm going to start to use that radius. So the radius is just kind of like a rolling pin. So we'll get it hot and we'll keep working on it. We just work back and forth like that until we get to the cross section that we want. So from here to this line right here is 10 inches. So that's probably what I'm going to shoot for.
You want that other piece in there?
What?
Another piece.
There is another piece in there. It's not going to hurt anything. Somebody will have. We'll put the other ones in a few minutes. So now I'm going to start working back up here a little bit. I'll turn this down, catch the edge of the anvil. Actually, now when I'm going to be on this side, I'm going to back up so that I'm not creating a notch on the side where I don't want it. A little bit cold, but I don't know if you can see how it was kind of, still had a little bit of color. I was able to keep it a little bit warm just by hitting it hard and fast.
We can fill that with sand.
Well, that would be a good idea probably.
No, maybe we can. We're going to see what's going on.
Yeah, that would be handy. So
it's not perfect, that's okay. But I wanted to get a lot of those deeper marks out from the edge of the anvil. And we can see from the notch, so I'm at about 7 inches long now. So these pieces were cut, most of them were cut at 6.5 inches long, and I left 2.5 inches for the blade. So you've got 4 inches. Would you like a knife for that? Okay. So I've got 4 inches that we're starting with to draw out to get. In my case, I'm going to shoot for about 10 inches long. Something else while that's warming up. Where's anybody know where my example piece went? Here it is. So something else to note is that this handle section does taper. We leave it a little wider here by the blade, and then it tapers out over its length. This is, say, roughly half the starting width. You know, these are approximate dimensions. This is not precision work. But you don't want this to get too thin or it'll be kind of weak. So kind of shoot for, you know, roughly half the starting width, and you should be in good shape. And then the thickness, in this case, the thickness is maybe just a little bit thicker than the starting stock. But if you aim to keep it close to the thickness of the starting stock, you'll be fine. And then when we get to working on the blade, we'll forge this to a taper. And that forging of the taper will elongate and give you a little bit longer blade, so that in the end, when the knife is all done, the thickest section will be right here at that transition point. Now I'm going to come back up to that shoulder again. Starting to form, and so as I see that forming, I'm trying to flatten that out so that it won't remain in the finished piece. Now, I'm just about down to the width that I want here. Just I have a little bit of extra width there that I need to take out, and the thickness is quite thick. So I'll be thinning that down to gain the additional length that I need. Quench buckets that we had from last week. Those will be handy to pull and floss the wheel on a little push down here. Now the other one fell out. figure out which is going to be best in each situation.
That's noisy.
That's fine. This is a place to keep the dogs.
The other ones have become oil.
Oh,
French puppies.
oil French buckets, okay, well, those have their place. So right now, I'm still a little bit thick here. I've got about the right width right at the transitions between the blade and the handle, but somehow the handle a little further along is still a little wider than I think that we need it, and I'm going to need to stretch that down a little bit more to gain the rest of the length that I need. Also, the very end, I'm going to forge to a more fairly thin cross section, and I'll gain quite a bit of length there too. We're almost there. Just a little bit more. Now, we're not going to do any quenching of the pieces right now. At the end, we will. I just got the quench bucket out just to keep the tongs cool because they're picking up some heat. So I'm going to take maybe just one or two more heats. I'm going to, on this next heat, what I'm going to do is I'm going to work the corners of the piece, so I've got a rectangular or square profile, but that will be kind of hard on my hands. So I'm going to tilt the piece at a little bit of an angle, and with some light blows, hit the corners to create just a bit of a chamfer or a radius there. And then I'll go and work on the very, very end. So I'm going to catch the shoulder down here and then just tilt this at an angle. Not trying to make it an octagon, I'm just trying to make it comfortable to hold on to. This one's twisted a little bit. I don't know if you can see that. I have a way to fix that. But when you do that, you end up with a little bit of like a burr almost on the edge. So you have to bring it back flat and just gently knock that burr off. Now, to take the twist out, we'll use the vise. Let me warm this up just real quick. And then what we can do is, I'm going to use this vise over here so I don't burn my arm. But what we'll do is we'll catch the end in the vise, clamp it, and then just twist it or untwist it as we need to get back flat. one more heat. I'm just going to work the very edge to get a flattened out profile. What you do with the end is up to you. A lot of the ones that I've made have a round profile that just kind of comes over into a little bit of a hook, or it will actually form a tiny little scroll with a little curlicue on the end. But that's a perfectly fine way to do this. I'm going to just do what I did last night, which was actually the first time I've made that particular variation on this. So with the blade edge, what will be the edge up, I'm going to just forge this flat. I'm going to just tap the now all I'm doing right now is just trying to make a nice graceful taper in the bit. That's all I'm going to do right now, because at this point we would go on to the blade. But I'm going to stop so that you guys can all get a chance to work, and then we'll see how everybody's projects are going. If we want to go to the blade, we'll do that, or we can save that for next week.